So to start it off, let's go through with what we meant by a concept of an electric field. Okay. Now, electric field is applied for when you have charges, positive charge and negative charge. So for charges, we will normally say that they tend to exert forces on each other, but the nature of the force can be repulsive or attractive depending on the sign of the charges. If your charges are like charges, meaning to say they're positive, positive, or negative, negative, they will tend to repel. But if they're unlike charges, meaning to say one of them is positive, one of them is negative, they will tend to attract. Now, this electric force arises because there's a charge inside the electric field produced by another charge. Normally, an electric field will exist around any electrical charges. If you put one charge inside the electric field of another charge, it will tend to experience an electric force. Okay, so when you're talking about electric field or gravitational field, for example, those are actually what we call fields of force. Fields of force is just simply a region where a force is experienced. Okay. So in your exam, when we define what is an electric field is just simply a region where an electric force is experienced by an electrical charge. Okay. And electric field may be represented by imaginary lines of force. It can be represented visually by lines called flux or field lines. So in the example below, you have some field lines and they are drawn differently depending on the system. If say you have an isolated positive charge, your field lines tend to be radial like this. Or, okay, this one is for isolated positive charge. But if you have an isolated negative charge, isolated negative point charge, your field line would also be radial like this. These are what you call as radial field lines. Okay. Then after that, the rest of these field lines systems that you see here, you don't really need to remember them. Only the first two is something that you need to remember, and the last one here. Okay, so there's also something called charge parallel plates, which is essentially just two plates that are parallel to each other and which carry some charge. So in between those two plates, you will also have an electric field being set up here. Because if you go and put a charge between this region, the charge experiences a force, so there is an electric field there. Okay, so for the case of charge parallel plates, your field lines would be something like this. They are equally spaced parallel lines. Okay, so the first two and the last few, you need to remember how they're usually shaped like. Okay, for the rest, not so. Okay, but you just do need to know a bit about the rules in how they are drawn, which will be discussed in the next page. So if you look at the third example, this one is, for example, a dipole system. You have a positive and negative charge here. This one comes about mainly due to the fact when you go and bring two charges close to each other. You imagine if you had the isolated positive test charge here and isolated negative test charge here, if you were to bring them close to each other, what will happen is that the two fields for the two charges will tend to overlap. So they combine and produce a new field. This is what you're gonna get. Okay. This one is called a dipole system. You have two different charges inside the system. All right. And then for the third and fourth one, the fourth and fifth example here, this is just an example of some other different field systems. Don't need to remember how they are drawn, but just remember some of the rules in which field lines are drawn. This one will be in the next page. Okay. So for electric field, the electric field has a certain direction to it. Okay. You draw lines to represent the field, but at the same time, you need to indicate direction of the field. So for electric field, the direction of your electric field is actually determined by the direction of force acting on a positive test charge placed inside the field. So for example, if you have the isolated positive test charge from before, I mentioned to you that the field lines will be radial, meaning to say they tend to come out from the same point. But how do I know it's supposed to be pointing outwards? In IGCSE, you would have remembered that when you draw the field lines for a charge, positive means will be going outwards, negative means will be going inwards, right? But how do I know for sure? What was the basis in saying that? It is actually determined based on the direction of force acting on a positive test charge. So for example, if I put a positive test charge here, here, and here, these are going to be repelled by the main charge in the center, right? So if you're talking about the electric force acting on the positive test charges, they will tend to be directed outwards like this. That's the reason why your field line will be having a direction outwards, because the direction of your field must follow the direction of force acting on a positive test charge. Okay, so you try to do the same thing for a negative test charge, like the ones that is situated here. Again, you put a positive test charge here, here, and here. You look at the direction of force acting on the positive test charge. Because this is positive and negative, the force acting on the test charge will be attractive by nature. So the direction of your force on the positive test charges will be inward. So the direction of your field would be directed inwards here. Okay. The field line remains radial as before, but this time the direction must be inwards. Okay. That is how we determine the direction of your electric field. Okay, so there are two main statements to always remember when it comes to direction of electric field. Field direction always follows direction of force acting on a positive test charge. But field direction would always be opposite to the direction of force acting on a negative test charge. So what do I mean by that? You look back at the diagram above. If say this time I have a negative test charge, say like this is my negative test charge. If you consider the force acting on the negative test charge, the direction of your force acting on your negative test charge should be attractive, so it will be directed inwards now. Now, if it's directed inwards, notice the direction of your force and the direction of your electric field, which you've already established earlier. They are acting in opposite directions, right? That's why we can say field direction is always opposite to the direction of force acting on a negative test charge. You can also see something similar in the second example here. If you consider that this is a negative charge at the center and this one is a negative test charge, the force experienced by the negative test charge should be repulsive, okay? But then when you look at the direction of your force and the field direction, again, it is opposite, all right? And then after that, you look at the third example diagram below. This one is for charge parallel plates. So as mentioned to you before, the field lines must be drawn parallel and with equal line spacing like this here. Okay, so field direction is determined by direction of force acting on a positive test charge. If this is your positive test charge, how do you know the direction of force acting on a positive test charge? You can just imagine that this one is positive, this one is positive, this one should by right be repulsive. And then this one is positive, but this one is negative. This one by right should be attractive. So when you consider these two cases, obviously your charge will be pushed downwards. There will be a force acting downwards, no doubt about that. Okay, so since the direction of force acting on positive test charge is downwards, the direction of your electric field therefore must be downwards, like this. And then if you have a negative test charge, like the ones that is being shown here, it will obviously be directed upwards, but again, it will be opposite to the direction of your field. Okay. Now, when you draw field lines, they are always drawn from positive to negative charge or from higher to lower electrical potential if there's no negative there. Let's just say, for example, from 100 volts to 15 volts. Okay, they must be in direction of decreasing potential. Okay, this one, in other words, is called in direction or decreasing potential. Okay. Then there are certain characteristics about field lines that you would need to remember, similar to that from gravitational field. Okay, so those few characteristics of the field lines are highlighted in green here. Those are the more important ones. Now, in the first place, field lines are supposed to be smooth curves that never cross or touch each other. Field lines can never ever touch or cross with each other. They can get very close to each other, but they can never be crossing. Okay. And then another important thing about field lines is that the spacing of your field lines is a measure of your field strength. It tells you how strong your field is. The closer the spacing of your field lines, the stronger the field strength, and vice versa, meaning to say the wider the spacing, the weaker the field. In the event that you have equal line spacings, that means that the field strength is uniform. Okay. Then after that, field lines must always be drawn perpendicular to a contacting surface. They must always make perpendicular contact with a surface. Cannot be at an angle to the surface. It must be at an angle of 90 degrees to the surface. Okay. And then lastly, the electric force acting on the charge at a point in the field will always be tangent to the field line at that point. Okay. You will make use of these 3 points most of the time when it comes to answering your exams questions. Okay. So let's look at the example for a dipole system here. If I ask you to predict the direction of force acting on some of the positive test charges placed here, here, and here, how do you know the direction of the force acting on them? Okay, so number one, for the positive test charge, if you refer back to this statement that I wrote much earlier, I mentioned to you that field direction always follows the direction of force acting on a positive test charge, right? You can also read it the other way around, where you can say that direction of force acting on a positive test charge follows direction of the field. Okay, it means the same thing. So if you look at the positive test charges that I've just highlighted below here in your dipole system, in general, the force must be following the direction of your field. So it should be pointing like this. Because you see, in your case, the direction of your field for the left-hand charge was something like this, right? So it must be pointing in that general direction. For the other 3 remaining charges, the field was going something like this, isn't it? So your force, electric force acting on the charges must also follow that general direction, okay? And then specifically, for each of the points that you have placed your positive test charge, the force must be tangent to the point. It must be tangent to the field line at that point. That's why you can see from here, your arrows are specifically drawn such that they are tangent to the field at the point where you place your positive test charge. Okay, that's how you will predict the direction of your electric force. Now, if you go and place negative test charges instead, say over here, you will still apply the similar logic here. But the thing now would be that for negative test charge, direction of force on a negative test charge will always be opposite to your field direction. Okay. So like in your case, if your field was like this, the field direction is going like this, the direction of force on your negative test charges must be opposite to the direction of the field. So it will be pointing in this general direction for the 3 charges here. And then other than for the bottom charge, your field direction is generally going in like this, right? Your electric force on your negative test charge must be opposite to it. So you get something like this, okay? But at the same time, the force, electric force, must be tangent to the field at the point where you place the charge. So it must be tangent like this, okay? So this is how you determine the direction of the forces on a positive test charge or negative test charge placed inside an electric field, okay? So then we move on to a next concept called electric force. Now, if you want to calculate the magnitude of the electric force acting on a charge placed inside an electric field, there's a specific equation and law that you tend to refer to. Okay. Now, in the first place, it was mentioned to you that electric force can either be attractive or repulsive depending on the charges that was used. The electric force acting between 2 point charges can be described using something called Coulomb's law, which basically states that the force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the separation. Okay, so if written in words, it actually means this. Fe is proportional to the product of charges QQ. Fe is inversely proportional to the separation square, so is Fe inversely proportional to R square here. If you were to combine both equations, you eventually get this equation. Fe is equals to QQ over R squared. So the proportionality sign here is the issue. You want to get rid of that. So you want to get rid of that, you introduce a constant. Okay, that constant is actually 1/4 pi epsilon naught. Okay, that is the constant here. Then you multiply with QQ over R squared. In summary, the electric force between 2 point charges is basically this. You need to remember this, okay? Now, you look at the constant that was just introduced there, you notice there's a new symbol there called epsilon naught. Epsilon naught is actually what we know as the permittivity of free space, or rather the permittivity of vacuum, which has this value. You can get it from the second page of your exam paper. It's inside your data sheet, all right? What is the actual definition, what it does, what is its actual physical meaning, you don't need to know. It's not covered inside your syllabus. You just need to know how to get the value from your data sheet. Okay, now sometimes in recent years your exam paper has actually made it easier. They've actually just listed for you directly what's this value, 1/4 pi epsilon naught. Again, it will be inside your data sheet. It's actually this value. Okay, now the Coulomb's law that was just described to you here only applies for point charges. Okay, point charges only. Point charge point charge is just simply a point that carries a charge. It has no size, it has no volume. All right. Now, for your questions, normally you can just assume subatomic particles like protons and electrons as point charges because they're very small. You can assume them to be just a point that carries a charge. All right. Now, for cases where you have something with size and volume and which also carry charges, you can only treat them as point charges under two specific conditions. If number one, their separation is large, or if number two, they are perfectly spherical. So let's just consider this little example here first. If you're talking about point charge, say this one is your positive point charge. Just now I told you it should not have any size or volume, right? It's just a point that carries a charge. So if it's a positive point charge here, your field lines will be radial. And the direction of your electric field should be pointed outwards, following the direction of force acting on a positive test charge placed inside the field. But you can always just remember it as, since it's a positive charge, it must always be pointing outwards. No problem there. So this one is for a point charge. If you have a spherical charge, we can actually say it's equivalent to a point charge. So let me just try and draw for you a spherical charge. Say you have a spherical charge that looks like this. This one has a size and volume. This one is a spherical charge. This one has size and volume. Okay. So one of the rules for drawing field lines, if you recall just now, I mentioned to you, you must draw the field lines perpendicular to each other. They must make perpendicular contact with each other. So if they need to make perpendicular contact with each other, the way you would draw your field line here would be something like this. Let me just try to draw it out here. It will be something like this. Let me find a suitable color. Okay, this one. It must be perpendicular contact always with your contacting surface. So if they make perpendicular contact with your contacting surface, this is how it will look like. It's also radial, okay? But at the same time, if you were to try to extrapolate the field lines into the sphere, you will notice that they seem to come from the center itself, from a particular point, just like that of a point charge. You see, for a point charge, it's just a point with charge. All your field lines come from one point itself. For a spherical charge, although you have size and volume there, but because you draw your field lines perpendicular to your contacting surface, you will notice that your field lines have the appearance of coming from the center, just like that of a point charge. That's why we can say that your sphere, if it carries charge, you can treat it as a point charge, okay? Now, then you can also, there's another criteria in which you can also say something as being a point charge. That one is by looking at the separation. So say, for example, I have something that doesn't look like a sphere, that looks like this. This is positive and this is negative. You look at this, these are not spheres, these are not point charges. And then additionally, their separation is considered to be quite small in relation with their size. So in your case here, this one, because the separation is considered to be quite small, this one is not considered as point charge. You cannot consider them as point charge because the separation is too small. But if you take the same charges and separate them so far off, let's just say all the way to the other end of this screen, in your current case now, this one, you will say that your separation is very large, okay? This one, your separation is very large with respect to the size of the charges here. So in this case here, you can actually assume them as being point charges, okay? So these are the only two conditions in which you can ever assume something to be point charges, all right? And another thing to note here is that the Coulomb's law that has been described to you here, notice that it has some similarity with what you've learned in gravitational field. Coulomb's law of force that has been described here is actually quite similar to Newton's law of gravitational attraction between point masses. It's just that they've changed the term from mass to charge, and the equation was changed accordingly from mass to charge. Okay, the only thing that is probably different is the constant that is used. They're using a different constant now. Okay. Then next thing I should mention to you is that what about, because you see Coulomb's law is only applicable for point charges. What about cases where your charges is not a point charge, but you still want to calculate the force acting on that charge? There's another equation that you can use. That one is this one. At any point in electric field with field strength E, your electric force acting on any given charge is usually determined by this. Fe is equals to the product of Q and E. Okay, where did this come from? It actually comes from the next quantity that we will be learning. Okay, so if you move on to the next page, we will go through something called electric field strength, E. Okay, now electric field strength actually gives you a measure of the electric force that will be experienced by a charge placed inside the field. The stronger your field, the stronger your force experienced by the charge, and vice versa. Okay. Now, for isolated charges, as I mentioned before, they have radial field lines. they are actually not considered to be uniform fields. They don't have a uniform field strength throughout, okay? Because if you look at the example below here, this is the positive test charge, this is the negative test charge. It was already mentioned that the field lines are radial by nature, like this. If I were to ask you whether the field strength around your isolated charge here is constant, is uniform, you cannot say so, because you look at the separation between your field lines. If you were to go away from the center of the charge, let's just say you're going in this particular direction, look at how the spacing between your field line changes. You see it gets progressively larger, right? You see your spacing here is actually increasing. This will tell you that your field strength is actually decreasing with distance from the center of your sphere. Okay, the same can also be said for your isolated negative charge here. All right. So because the field line spacing is increasing from the center, your field strength is actually decreasing. But when you're talking about charge parallel plate, the third diagram here, you can say that the field is uniform. They have constant field strength, they have uniform field strength because the line spacings are always parallel and equally spaced. Okay, so this is your charge parallel plate. You will notice that all your lines are just parallel with equal spacing. So the field strength anywhere inside this region or in between the place will always be constant. Okay, so this one here, you could say constant spacing, E constant. Okay, so that is how you look at field strength if just by looking at the field lines itself. Now, by definition, electric field strength in your exam is defined as this. It is the force acting per unit positive charge. It is very important that you include the term positive here. Okay, because field strength being a vector would usually have direction. Your direction is always based on what happens to a positive test charge that you place inside the field. That's why it's important to put this term in. It's the force acting per unit positive charge. So if you want to write it in an equation form, it just simply means this. Field strength is Fe over Q. Okay. From here, you will get Fe equals to QE. That's the reason why in the previous page just now I mentioned to you, you want to find the electric force acting on any charge, you use Fe equals to QE. It's because it came from this particular equation here. All right. Now, there's another different equation that can also be used to represent electric field strength. This one, if you recall what you learned in the previous page, it was mentioned to you that electric force between 2 point charges can be given by 1/4 pi epsilon naught over Q multiplied with QQ over R square, right? Since field strength is Fe over Q, you just substitute this thing in to Fe here. You try to simplify it, you will notice that the small q will tend to cancel each other off, eventually giving you this expression. Field strength is actually 1/4 pi epsilon naught Q over R squared. Okay, so there are two different equations that you tend to use when it comes to calculating electric field strength. Which one you will use depends on the context of the question that you will encounter. All right, so one thing to note here, a few things to note here actually, is that field strength is also considered to be a vector. All right, the direction of your field strength will always be in the same direction as the electric field. Okay, and field strength around a charge is normally inversely proportional to the square of the distance of the charge. It follows what we call an inverse square law. What this means is something like this. If you look at this original equation here, if everything else remains constant, E is actually inversely proportional to R squared. Okay, it's inversely proportional to separation square. This is what we call as inverse square law. All right. And another thing to note here would be this. You will notice that when you look at both of this equation, there's actually the term for Q there. For the first one, the Q is at the bottom. The second one, the Q is at the top. All right. So how do I distinguish between these two charges? Always just remember this now. The charge term small q at the bottom of the equation is normally the test charge that you place inside the field. Whereas the big Q that you often see at the top of the equation is normally the charge that produces the field itself. Okay, so to give you an idea how this one will be applied, you look at this little diagram that you have here. Say this one right now is some sort of charge or positive charge. It produces electric field, so we call this big Q here. And then after that, at some distance away from that charge, we're interested to find the electric field strength. Let's just say I'm interested at this particular point here. I want to find out what is the electric field strength at this point, at a distance of r from the charge itself. So if I want to find out the electric field strength at this point, you can use two different equations. The first one would have probably been E equals to 1 over 4 pi epsilon naught Q over R squared. The Q here is the charge producing the field. The R here is the separation between that charge and the point that you're considering. Okay. Then another different equation that you could have used here to find the electric field strength would be this. E is equals to Fe over Q. So in your case, if you wanted to use this, you would actually have to place a test charge, small q here, and then you will need to find out what is the electric force acting on that particular test charge. Say maybe this one is experiencing an electric force of Fe in this direction. You need to find out what is the test charge you place inside the field. You need to find out what is the electric force acting on that test charge. So if you take Fe over Q, that one will be the field strength at that point. Okay. So that's how you would use these two equations. In summary, this one will require a test charge. Now, simply put, this one requires a test charge in order to find the field strength, but this one doesn't require a test charge. Okay. Now, just now I mentioned to you that field strength is a vector. So when it's a vector, you need to consider direction. In the event that you have two overlapping fields that create a new resultant electric field, your resultant field strength that you calculate, you need to consider the direction. Okay. So this one will be something that I'll explain more after I go through some past year question examples with you.